In this next example, we'll be looking at problems that are involving right triangles and the Pythagorean theorem. The idea behind this is when we have a problem like this where maybe we have one vehicle moving towards or away from an intersection and another object moving towards or away from something. And this object may be moving at different rates, and we know their rates with respect to their change to the origin. But what we want to find is the rate of change of the length of this side. So this might look something like this. As they're moving away, moving in different speeds, the rate of change of this hypotenuse here is going to be different depending on where we are. Also, it's going to depend on which direction these objects are moving. One thing to remember here is when we're moving away from the origin, that would be a positive value because our distance is increasing. But when I'm moving towards the origin, like I'm doing right now, this is actually a negative value because my distance is decreasing. So in this problem we have a highway change. So the police officer is approaching the intersection and a car is going away from the intersection. The police officer wants to know how fast this vehicle is going to know whether or not he should give him a speeding ticket. What we do know is some information about where these vehicles are. For one thing, the cruiser, that's the police car, is 0.6 miles away. Notice that's a changing value because he is approaching, and so we're not going to treat that as a constant. We're going to have to use it later. The car is moving away and it's 0.8 miles away, and again it is not a constant because the car is moving. What we don't know is the z here and how far apart they are, but we can find that using the Pythagorean theorem. We can also look at the speed of the car. It says that the distance between the car is increasing at 20 miles per hour. Basically, the police officer is using his radar and he's measuring that car going away from him at a rate of 20 miles per hour. Since this is looking at z, this is the rate of change of z, that would be dz with respect to time. It's going to be a positive value because that car is moving away. The police officer also knows how fast he's going. He's going 60 miles per hour. He's approaching the intersection, so that's going to correspond to y, and so our dy dt has to be a negative value. Now, they didn't tell us this is negative. We have to interpret that on our own because we know that we're approaching the origin and y right now is decreasing. What we're asked to find then is the speed of the car. The speed of the car would be going with x here, and so that would be dx dt. Now, how are all of these connected? That's what we need to find out. Well, it's a right triangle, so we're just connected by the Pythagorean theorem. And so if I take my derivative implicitly with respect to time, we get this equation, and now we want to start plugging in the values that we have. Now we know at this instant we're at 0.8 for x. We're looking for dx dt. We also know at this instant that y is 0.6, and the rate of change for that was negative 60. Here we get a little hung up because we don't have a value for z yet. We do have a value for dz dt, which was 20. So we need to go back and find z. Again, these values are connected by the Pythagorean theorem. So if I know that this is 0.8 and I know that this is 0.6, then I also know that 0.6 squared plus 0.8 squared will be equal to z squared. And we find at this moment, this instant, z is going to be equal to 1. And so we can plug that 1 in. Sometimes we'll need to find more variables using how they're connected. But we just need to make sure that we can get this down to the one thing that we're looking for. If we multiply this out, this is going to come to 70 miles per hour. Oops, sorry, I'm looking at the wrong problem. Okay, working this out, this is going to be 1.6 dx dt plus 1.2 times negative 60 is equal to 40. So we've got 1.6 dx dt is equal to 112, and dx dt is equal to 70. Now we need to put units with this. Everything's in miles an hour, so this is miles per hour.